Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll discuss how to evaluate linear regression models in sklearn. Let's look at general steps in model evaluation. We first split the data into training and test. For that, we use train_test_split class from sklearn.model_selection module. Train_test_split takes the feature matrix X and label vector Y, or it could also be label matrix in case of multi-output regression, and a random seed, and it returns the train feature matrix, test feature matrix, train labels, and test labels. We fit the linear regression estimator on the training set. We calculate training error, which is also called as empirical error, and finally we calculate test error, which is called as generalization error. Then we compare training and test error to understand whether our model is a right fit or whether it is underfitting or overfitting. So let's study how to evaluate trained linear regression model in sklearn. sklearn provides score method on estimator objects. We are going to use this score method for evaluating the trained linear regression model. So what we do is we call the score method on the regression estimator. We supply the feature matrix and a label vector or matrix of the test set, and the score method returns a quantity which is known as R square or coefficient of determination. Let's see what this R square is. Let's see how this R square is computed. So R square is computed as 1 minus u by v, where u is residual sum of squares. And this is a familiar equation to us. Xw gives us the predicted labels, y is the actual label, and this is nothing but the difference between the predicted label and the actual label. We take the transpose of this difference set and multiply it with itself. So this is like finding the square of difference between the predicted labels and the actual labels, which is what is the loss function for the linear regression. On the other hand, v is total sum of square. And this v is computed as a difference between the actual label minus the mean of the predicted label. We take transpose and multiply this difference vector with itself. So this is square of difference between the actual label and the mean of the predicted label. So here it was the predicted label, but here we take mean of the predicted label, and that's how we calculate what is called as sum of squared errors. So now this is also sum of squared error, but this is sum of squared error between actual and mean predicted label, whereas u is sum of squared error between actual and the predicted label. So R square has the best possible score of 1. A constant model that always predicts the expected value of y would get score of 0. And this score can be negative because model can be arbitrarily worse. Let's see when these scores occur. So we get score of 1 when u, that is the sum of squared error, is 0. So when u is 0, obviously this quantity is 0, so 1 minus 0 is 1, so we get R square of 1 when u is equal to 0. A constant model that predicts the expected value of y would get score of 0, and that would happen when u is exactly like v. This is the total sum of squared error, and this is the residual sum of squared error. For this we calculate, this particular quantity is calculated as the difference between the actual label minus mean of the predicted labels, and this quantity is calculated as the difference between the predicted label and actual label, and then we square it up. So when the predicted label is exactly equal to the mean of all predicted labels, we'll get into a situation where u will be exactly equal to v. And when that happens, this quantity becomes 1, and 1 minus 1 becomes 0, so r square returns the value of 0. And if model is arbitrarily worse, u is expected to be greater than v, and then the score can become negative. So apart from score, so score method returns r square. But there could be other regression metrics that could be of our interest. Fortunately, sklearn provides a bunch of such regression metrics for us to evaluate performance of the trend estimator on the evaluation set. Let's look at those evaluation metrics. The first one is mean absolute error. So all these metrics are implemented as part of sklearn.metrics module. We can import these metrics one by one. So from sklearn.metrics import mean absolute error, and we calculate mean absolute error by supplying the actual labels and the predicted labels. So this particular function would return the score, that is mean absolute error between the predicted values and the actual values. In the similar manner, we have mean squared error, which is again implemented as part of sklearn.metrics package. And we calculate this mean squared error exactly like mean absolute error, where we supply the actual labels and the predicted labels. So you can see that all these metrics need two arguments. One is the actual label and second is the predicted label. And then that particular metric is applied on the supplied arguments, and we get the evaluation score. Then there is R2 score, which gives same output as the score method. And this R2 is exactly what we saw in the previous slide, which is the coefficient of determination. So we import R2 underscore score from sklearn.metric module, and we supply the actual values and the predicted values to obtain the R2 score. So all these metrics can also be used in multi-output regression setup. Then you have additional metrics that are not amenable to multi-output regression setup. So one is mean squared log error, and this particular metric is useful for targets with exponential growth. So when our labels denote exponential growths like population, sales growth of a company, etc., then we use mean squared log error. So this particular metric penalizes underestimation heavier than the overestimation. Then we have mean absolute percentage error, which is sensitive to relative error. So when we want to evaluate our predictions that are sensitive to relative errors, we should be using mean absolute percentage error. We also have mean absolute error, which is robust to outliers. It doesn't give a lot of importance to the outliers, and our evaluation becomes robust to the outliers. So let's see how to evaluate regression model on worst case error. So we can use metric max underscore error, which gets us worst case error. Let's first calculate worst case error on training set. So we import max underscore error from sklearn.metrics, and we supply the actual values and the predicted values. In this case, we supply the training labels and the predicted training labels. and we calculate the worst case training error. The worst case error on test data can also be calculated in a similar manner, where we supply, instead of training, we have supplied test labels and the predicted test labels to get the worst case error on the test set. This matrix can only be used in single output regression. It does not support multi-output regression. So while studying these metrics, you will come across two terms, the ones that are ending in scores and the other metrics that are ending in errors. So score is a matrix for which higher value is better, and error is a metric for which lower value is better. So let's keep this convention in mind while evaluating regression models, or for that matter any other estimator in any other estimator class. So we convert error metric to score metric by adding neg underscore suffix. For example, these are some of the error functions that are there in sklearn, and on the right hand side we see the corresponding scoring functions. For example, mean absolute error is the error function or is the error metric that is defined in sklearn.metrics module. The corresponding scoring function is neg underscore mean absolute error. So you can see that we have added a neg underscore suffix to this particular error metric and we got this particular scoring metric. And you can see that pattern getting repeated throughout this table. So for mean underscore squared underscore error, the corresponding scoring metric is neg underscore mean underscore squared underscore error. Then we have similar corresponding scoring metric for mean squared error, mean squared log error, and median absolute error. So now, in case when we get comparable performance on training and test set with a particular split, is this performance guaranteed on other splits? So you remember, right? I mean, we use train underscore test underscore split function to get a split on training and test set. That was a single split that we got. So what is a guarantee that the performance that we have gotten on this training and test split is also replicable or is also guaranteed on other splits? So there are a couple of questions. Is the test set sufficiently large? In case the test set is small, the test error obtained may be unstable and it would not reflect the true test error on the larger test set. Second question is, what is the chance that the easiest examples were kept aside as test? And if this happens, we would get optimistic estimation of true test error. And both of these situations are not really good as far as evaluating the generalization error or the test error of the model. And they will not give us the right kind of estimate about how model will perform on unseen data when deployed. So we need something better, and fortunately we have a cross-validation tool. We have studied cross-validation in detail in machine learning techniques class, and here we'll use this cross-validation. So cross-validation, what it does is it creates multiple training and test sets, and it evaluates the performance on different test set. That way we are using different test splits, and hopefully when we perform this evaluation on multiple test splits, we get robust performance evaluation. So cross-validation performs robust evaluation of model performance by repeated splitting and providing many training and test errors. This enables us to estimate variability in generalization performance of the model. So sklearn implements the following cross-validation iterators. Right? So we need to know how to perform these splits, and there are various ways in which these splits can be made. And sklearn implements different cross-validation iterators. So there is this k-fold cross-validation iterator, which is very similar to what we have studied in machine learning techniques course, where we divide data into k different folds or k different partitions, and then we select k minus 1 partitions for training and 1 partition for test or for evaluation. And we do this for different splits of these k partitions. That way we get multiple training sets as well as evaluation sets. Then we have another iterator called as repeated k-fold. This essentially repeats the k-fold splitting. Then we have leave one out, which is a special case of k-fold where k is equal to number of training samples. So in leave one out, we leave out exactly one example as a test, and we use rest n-1 examples for training. So we get n such different splits on which we can perform training as well as the evaluation. And finally we have shuffle split, which shuffles the training data before splitting, and it does a random permutation of the data points and create training and test sets. And it does it repetitively repetitively for a specific number of times that is specified by the user. So let's try to find out how to obtain cross-validated performance measure using k-fold. So here we use a cross_val_score API implemented in sklearn.model selection module. So we have linear regression estimator, and on this linear regression estimator we want to calculate cross-validation score. So we provide the name of the estimator, the feature matrix, the label vector or label matrix depending on what kind of regression problem we are solving, and we also specify number of folds in cross-validation. When we specify an integer value to the CV parameter of cross-validation score, it uses k-fold cross-validation iterator and divides the training data into the specified number of folds. It uses 4 folds for training and 1 fold for evaluation. There is an alternate way of writing the same thing, where we will be explicitly be using k-fold cross-validation iterator. So we import k-fold from sklearn.model_selection module, and we instantiate an object of a k-fold iterator by specifying number of splits and a random seed. Then in cross-validation score, instead of specifying an integer value over here, we specify the k-fold object. And when we specify this k-fold object, it performs the k-fold, it actually does the cross-validation with k-fold iterator. So these two code snippets exactly do the same thing. In case we want to use different cross-validation iterator, we can simply choose one from the model_selection module, instantiate that object, and specify that cross-validation iterator in the CV parameter of cross-validation score. Let's see a couple of examples of that. Let's first see how to use leave one out cross-validation iterator for calculating the cross-validated performance. So here we import leave one out class from sklearn.model_selection module. So you can see that all model selection related utilities are present in model_selection module of sklearn. And this is because of the design principles of sklearn API that we studied in the first week of machine learning practice course. So here what we do is we instantiate an object of leave one out cross-validation iterator, and that object is used as a parameter for the CV parameter. That object is used as a value of CV parameter in cross-validation score. So when we when we execute this particular statement, we get a score that is calculated using leave one out cross-validation iterator. Now this is same as using k-fold cross-validation with number of splits equal to n, which is essentially the number of samples in the training set. So here what we do is we first calculate the number of samples in the training set and we set n splits to n in k-fold cross-validation, and then we calculate the cross-validation score with the object of k-fold cross-validation iterator as the value of CV parameter. Again, these two code snippets would do the same thing. Let's look at how to obtain cross-validated performance using shuffle split. Again, the strategy is the same. We import shuffle split, we instantiate object of a shuffle split by specifying number of splits, the size of the test, and a random seed. And we use that shuffle split object as the value of the cross-validation parameter in cross-validation score function. Shuffle split is also called as random permutation. It generates user-defined number of trained test split as specified in n_splits, and it is robust to the class distribution. So even if there are different class distributions, if you do not have uniform class distribution, even in that case, shuffle splits work reasonably well. In each iteration, shuffle split shuffles order of data samples and then splits it into training and test. So far we were using default scoring mechanism for calculating cross-validation score. Now here we'll try to specify different scoring mechanisms. So we have already seen some of the scoring metrics which correspond to error metrics before few slides. So scoring parameter can be set to one of the scoring schemes implemented in sklearn. So we can use max error, R2, or all these negative of the error metrics, that is negative mean absolute error, negative mean squared error, negative mean squared log error, negative median absolute error, and negative root mean squared error. So we can substitute these values in the scoring parameter and we get that particular score by after doing the cross validation. So since we are doing cross validation, hopefully these scores are robust than calculating these scores just on a single training and test split. Let's see how to obtain test scores for different folds. So here what we have done is we have used shuffle split cross-validation iterator with number of splits to be 40, size of the test is 30%, and random seed equal to 0. Then we calculate then we call a cross-validate function. So instead of calling cross-val score, we are now calling cross-validate function with parameters, which is the estimator, which is a regressor, the data, which is a feature matrix, target is the label vector or matrix depending on whether we are solving single or multi output regression problem, then the cross validation iterator, and we also specify the scoring scheme. Now this cross validate returns this result, which is essentially a Python dictionary with the following keys. It has got fit time, score time, test score, estimator, and train score. Estimator and train score are optional, and in order to obtain them, we need to specify additional parameter to cross-validate. By default, we do not get estimator and train underscore score. So fit underscore time gives the time that was required for fitting that particular training, for fitting the regression model on that training set. Score time is the time it took to get the score on the evaluation set, and test score is actually the score that was obtained on that particular evaluation set, and this score in this case will be negative mean absolute error because that is what we have specified in the scoring parameter. In the same manner, we can also obtain trend estimators and scores for each fold. For obtaining trend estimator, we need to set return underscore estimator parameter to true. It is false by default. For scores on the training set, we need to set return underscore trend underscore score parameter to true. Let's look at an example. So here we are calling the cross-validate function by specifying all those parameters that we saw in the previous slide. In addition to that, we are specifying a couple of more parameters, which is return underscore trend underscore score, setting it to true, and return underscore estimator, and also setting that to true. When we do this, we get, in this particular dictionary, which is CV underscore result, we get different estimators that were trained on different splits. We also get the training scores. That helps us to compare training and test scores, as well as we can also examine these estimators that were run, that were learned on different splits. The estimators can be accessed to estimator key of this dictionary. So cross-validate function also allows us to specify multiple scoring metrics. This facility is not available in cross-validation score function. So that is the main difference between cross-validate and cross-validation score. Cross-validation score also only returns the score on that only returns a score after cross-validation, whereas cross-validate returns a lot more information, like it returns the score for every fold. It also returns the estimator and the training error that it obtains on different folds while performing cross-validation. So in this case, we have specified a couple of scoring parameters. One is negative mean absolute error and negative mean squared error. So let's see how to study effect of number of samples on training and test errors. So sklearn provides us with learning underscore curve class. This learning underscore curve class takes estimator, training data, size of the training, cross-validation strategy, and scoring scheme as arguments, which is pretty much same as the cross-validate function. So we instantiate an object of learning curve by specifying the linear regression estimator, training feature matrix, label matrix, the size of the training data, then the cross-validation iterator, and the scoring scheme. And we can get the training size, training score, and test score by accessing first three values of this particular results that was written by learning underscore curve. We can convert, since these are scoring schemes, in this scoring we are using basically the negative of error. So in order to obtain the actual errors, we multiply each of these scores by -1. So we multiply the train score by -1, we get train error. We multiply test score by -1, we get test error. This is how you can convert scores into errors if you want to output the error due to a specific training or specific evaluation set for that estimator. In step 2, we generally plot training and test scores as function of the size of the training set. And this plot helps us to make assessment about the model fitment. We can diagnose whether model is just a right fit or whether it is underfitting or overfitting, and then take appropriate measures to alleviate any of such kind of fitment concerns. In order to perform underfitting and overfitting diagnosis, we have this four-step process which we have also studied in machine learning techniques course. We'll repeat, we'll revise it over here, and in the collab we'll actually implement this and experience how it works in sklearn. So here the first step is to fit linear model with different number of features. For each model, we obtain training and test error, and then what we do is we plot number of features versus error graph. And in this error graph there will be two curves, one for training and second for test errors. We examine these graphs to detect underfitting or overfitting issues. So we can replace this number of features that we are using here in the step 1 with any other tunable hyperparameter. And when we do that, we are able to find out whether the model is underfitting or overfitting, or whether that's the right fit for what kind of values of that hyperparameter. And then we can set the appropriate value of the hyperparameter such that we are getting optimal evaluation error on the test set. So we can follow this particular general process in order to tune the hyperparameters.